Welcome in the series of lectures on structural equation modeling. In the previous lecture, I tried to explain the concept and meaning of the structural equation modeling and introduce the various technical terms and the various types of models that are being used and tested using this approach. Today, I will discuss the various procedural steps, how we actually do the structural equation modeling. But this discussion will be not based on any specific software, but it will be a generic theoretical lecture in which I will try my best to make the things clear how actually we proceed when we do structural equation modeling. But before I go to the procedural steps, I would like to recap, I would like to redefine. As you know, that there is a difficulty in defining the term structural equation modeling or this approach in itself because this is a set of statistical procedures, set of statistical tools and techniques that are used to test the structural models. And when I say structural models or the structure, then it simply means that the pattern of relationship among the variables which we are studying. For example, you can see on this starting screen that there are several different color balls connected to each other. If we assume that these balls are some of the psychological, sociological, or other types of variables, and we are defining that these, for example, these two red balls are related to each other, these two light blue balls are related to each other, but these two balls are not related to each other. Similarly, if we have a predefined or based on any theory, a pre-specified pattern of relationship among variables, then that pattern of relationship among the variables itself is called structure. And these relationships can be represented in terms of equations. And therefore, structural equation models are basically the models or the equations representing the pattern of relationship depicted or presented in any structural model. So again I would reiterate that the meaning of the term structure in the structural equation modeling is very simple, that it is a pattern of relationship, how variables interrelate with each other. Some variables may be causing the other variables, they may be interdependent with each other, some may be uh, co-varying together, they or a set of all these types of relationship may exist among the variables. So whatever we believe that how the variables under study are related with each other, whether they are interdependent, whether one is causing the other, or whether there is a sequence of causation, that one is causing the second variable, second is causing third, third is causing fourth, and the first and the fourth are also causally linked. Likewise, we can believe definitely based on some prior theory or prior researches or our own research experiences. But when we assume or believe that variables are related in a specified pattern of relationship. That pattern of relationship among variables is a structure. And the second thing is that those structures, those pattern of relationships can be represented in terms of equations, very similar to the regression equations. And therefore, the structural equation modeling is basically a set of statistical procedures to test the predefined, pre-hypothesized pattern of relationship among variables, that is the structural models, and the whole set of techniques taken together will represent a statistical approach which is called structural equation modeling. And in this lecture, I will try to explain how the pre-specified or pre-hypothesized uh, structures or the pattern of relationships are tested using the structural modeling approach. But remember, this is not one statistics. This may include a set of statistical approaches or techniques or processes. And for further details on the conceptualization of this term, I would suggest to go through my previous lecture, which is basically focused on explaining these concepts. Now, quickly review some more aspect of the structural equation modeling. As I said, that structure in structural equation model or modeling may be conceptualized as the pattern of relationship among variables, how the variables are believed to be related with each other. Now, the in previous lecture, I explained that the variables may be observed or directly measured variables, or those variables may not be directly measured, but they are like factors which are reflected by some observed variables, and they are called latent variables. So, the structure or the structural relationship may involve the relationship among variables, whether observed or latent or both, and they may be linked in a causal pattern or in any other pattern. And this type of structure, when we link the observed or the latent or both observed and latent variables in some pre-specified causal sequence, causal pattern, then these models are called structural model or structural relationship model in the terminology of SEM. And this pictorial depiction is one example of the structural relationship model. All the variables are represented in rectangles, therefore they are observed variables, and these small circles with the arrowhead, they represent the errors or the disturbances. And I explained the difference between errors and disturbances also. Please watch my earlier video. So this model is basically structural relationship model or a structural model where the first observed variable, which is not being caused by any other variable, therefore it is exogenous variable, and this exogenous variable is bringing or is believed to bring change in these three variables, and in turn the first two variables, that is this one and this one, are bringing change in this final variable. But remember that this is not assumed to bring any change in this third variable. We may also assume that this is bringing, so the pattern of relationship may be of any kind. But this is one specified pattern of relationship, and this model will be called structural relationship model or structural model. And we can represent, say, if this is x1, this is x2, and this is y, then we can represent beta 1 x1 plus beta 2 x2 is equal to y. So all these paths and these connections are often referred to as paths. All these paths can be translated into different equations. For example, this is one single path. We can represent this with one equation, this one with one equation, the path originating from here, then going from here to here, may be represented with another equation. And therefore, we are testing a number of equations. We are trying to solve a number of equations simultaneously. And therefore, I prefer to, and this is a mnemonic. SEM is basically called structural equation modeling. But we can consider it as a simultaneous equation modeling because we are simultaneously modeling different uh, structural relationship equations. But there may be other type of model which is called measurement model, in which variables may be linked with one or more latent variables, that is called factors. The unobserved variables, and unobserved variables are generally represented by oval. You see this picture. So this is one factor, say this is intelligence, and these are the indicators, say reasoning, working memory, and say visual reasoning, and this is verbal reasoning and working memory. These are three indicators, and it is assumed that intelligence, this factor, this unobserved variable, is bringing variations in these observed variables. So this pattern of relationship, this is again a structure, but this structure is called measurement structure or measurement model. So in structural equation modeling, we basically test different types of models. Even if we obtain data in a time series or in a longitudinal design, the growth curve modeling is also possible. So there are different applications of structural equation modeling. The two major applications that in the field of psychology we often encounter is the measurement model and the structural model. So I will briefly describe these two models. So structural equation modeling for our purpose may be a measurement model, and generally this measurement model is called confirmatory factor analysis. In this, we believe that certain factors are linked with certain pre-specified indicators, and we define the factor structure. For example, big five model of personality. So there are five latent factors, and each of them are having predefined indicators, predefined traits associated with them. And when we test this type of model, then this is basically a confirmatory factor analysis. We are trying to confirm whether the big five model reported by Costa and McCrae is really valid or not, whether it is fitting with the data, say, obtained in India or not. So when we are trying to do this, we are trying to test a structural equation model that is called measurement model, and the approach is generally called confirmatory factor analysis. So confirmatory factor analysis is one application of the structural equation modeling, and that we often encounter, and you might have heard this term very often. In structural relationship model, the models may be of different types. Path analysis is one example of the structural relationship. I will go to the previous slide. This is basically a path analytic model Why? Because you know that all the variables are observed variables. But when the similar relationship model is depicted in which some of the variables are latent variables represented by ellipse or these uh, uh, oval shapes, then that model is also a structural relationship model, but that is not called generally path analysis. So some authors prefer to make this distinction. So a structural relationship model is basically a model in which we believe that certain variables are causally linked with each other in a predefined sequence or manner, and when we test this pattern of relationship among variables, then that application is called path analysis. And generally, it is believed, and many authors assume, that path analysis involves only the observed variables, whereas the broader class that is called a structural model or a structural relationship model, that may include both observed variables as well as latent variables. So, the path analysis is a specific case or a specific example of the structural model or structural relationship models. This model basically models the structure, that is the pattern of relationship among a given set of variables. And sometimes this relationship structure may involve mediator variables and sometimes moderator variables and sometimes both mediator and moderators. When I am saying mediator variables, if you are not aware, then simply this mediator variables are like third variables which are causally linked between the two variables. For example, the classical example is SOA. There is a stimulus, and this stimulus influences the organism, and then organism in turn makes a response. So, the stimulus response relationship is basically a mediated relationship through organism. So we can model this type of mediated relationship also, and we can test using the SEM approach. Sometimes we believe, for example, stress and health, and we believe that in general, stress has a very strong negative relationship with health. If stress is high, the health will be poor. But if few individuals are having high levels of, say, social support, then despite high stress, they are likely to have less impact on their mental health. So we can say that social support is moderating or buffering the effect of the stress on the health or mental health. So we can test this type of moderators also in this relationship, and moderators are generally represented in the structural equation model as the product of the moderator variable and the predictor variable, that is also called independent variable. So to summarize this structural relationship model, of which path analysis is one example, basically test a model of relationship among variables, assuming that the variables are causally linked with each other in a predefined manner or pre-hypothesized manner. Now coming to the measurement model, and the measurement model generally involves confirmatory factor analysis. However, the structural equation modeling approach may be used for exploratory factor analysis also. So the factor analytic model focuses solely on how the observed variables are linked to their underlying latent factors. For example, reasoning, working memory, and reasoning may be verbal reasoning, visual reasoning, and working memory. Say these are three indicators, three observed variables that we can measure using some psychological test. And we assume that these three variables are linked with an underlying construct that is called intelligence. So, the factor analytic model, the confirmatory factor analytic model, basically aims at testing how the observed variables are linked with their underlying latent factors. So, factor analysis is basically concerned with the extent to which the observed variables are generated, are caused by the underlying latent constructs. And when we assume that the latent variable, that is the factor, for example, intelligence, is causing variation in our reasoning, working memory, or other indicator of the intelligence, then such measurement models or factor analytic models are called reflective factor analytic models. And the major focus of this analysis is getting the strength of the regression paths from the factors to the observed variables. So when we will pictorially depict this model, the arrow-headed line will be moving from factor to the observed variables. The arrow will be pointing towards the observed variables. And the regression coefficient, the standardized regression path coefficients are generally considered as factor loadings. And these are of the primary interest. However, sometimes we assume that variations in the latent factor is because of the observed indicators. For example, if I am having high education, my income is high, then my socio-economic status is also high. So my education, level of education and my income is determining my socio-economic status. So the path is moving from observed variables. What we observed? You observed my education level, you observed my income level, and then you determined my SES. We never measure SES directly. The SES is measured indirectly by measuring the education, income, and many other indicators. So, if latent factors are assumed to be caused by the observed indicators or the manifest variables or the observed variables, then that is also a measurement model, factor analytic model, but that factor analytic model is called formative factor analytic model. And these models can also be tested using the structural equation modeling approach. Sometimes we also find interesting to assume that the various factors in a factor analytic model are related with each other. For example, if there are 5 domains of personality, and we may assume that all the 5 domains of personality are correlated with each other. So sometimes we model this interfactor relationships also, and we can develop a model in which the factors are interrelated or co-varying with each other, or we can develop a model in which we assume that factors are orthogonal to each other, they are not having relationship with each other, and therefore we will omit this regression structure among the factors. So this is just brief introduction. whenever in the next few lectures I will be trying to show you how actually we do these types of analysis using some software. Basically, I'll focus the analysis using MOS, then I will explain it a little bit further. Before I proceed, let us have a very quick overview of the confirmatory versus exploratory factor analysis. Confirmatory factor analysis is basically a type of structural modeling approach. So whenever you will study confirmatory factor analysis, it is most of the times clubbed in the main heading of structural equation modeling, whereas exploratory factor analysis is treated independently, slightly different from this structural equation modeling approach. However, it doesn't mean that using SEM we cannot do the exploratory factor analysis. It is possible, but it will take time because it is a very long and iterative process. Since it is exploratory, we do not know which indicators are associated with which of the assumed latent factors. What we actually do, that we allow the latent factors to be linked with all the observed variables, and then we test the model, then we remove some of the paths, then we change the path. Suppose we are linking a variable ex to the latent factor a, but if it is not providing a good fit, then we will try to link it with factor b, and if it is providing good fit, we will retain. So it will be a very long iterative process, and using a structural equation modeling approach, we can arrive at exploratory factor analytic findings also. But generally there are different other approaches which are available in the statistical softwares also, and we can do it in a different way. So generally we do not prefer exploratory factor analysis using structural equation modeling approach. Here we try to validate or test a predefined factor structure, whether this predefined factor structure is fitting with the data or not, whether it is valid or not. So basically, in this sense, exploratory factor analysis is different from confirmatory factor analysis. The confirmatory factor analysis tests the explicitly stated hypothesis. And when I am saying explicitly stated hypothesis, means we explicitly predefine that which latent factor will be related with or linked with which of the indicator variables or manifest observed variables. And then using SEM approach, we test whether this model is fitting with the data or not. So if we have to summarize, we can say that exploratory factor analysis is basically a data-driven approach. We do not have any predefined structure beforehand. We don't know what is the how the variables are related with which latent factor, and we start with data and arrive at a theory or a latent factor structure model. Contrary to it, the confirmatory factor analysis begins with a hypothesis. It is a hypothesis-driven process where we already know that how the variables are related with the latent factor. And only we try to test whether the hypothesis stands valid or not, whether the hypothesis can be retained or not. So in this sense, exploratory factor analysis is a data-driven approach, whereas confirmatory factor analysis is a hypothesis-driven approach. Let us have some quick comparison on other things. Uh, I will explain constant when I will be explaining the procedural step, but We do not constrain any of the paths, any of the link or relationship in exploratory factor analysis. But in confirmatory factor analysis, these constraints are imposed. For example, uh, we fix the path coefficients to 1 of each of the marker variable of a given latent variable. But such paths are not fixed to 1 in exploratory factor analysis in general. Similarly, unstandardized solutions are generally not applied or not applicable in exploratory factor analysis, though it is possible. But in confirmatory factor analysis, we get both standardized as well as non-standardized solutions. So the standardized solutions that generally is available in exploratory factor analysis is nothing but the factor loadings. And similar factor loadings are also possible in confirmatory factor analysis, but there is some additional feature that we can also get the unstandardized solution, the raw score regression coefficients also in confirmatory factor analysis. Similarly, in exploratory factor analysis, first we extract the factor and then to interpret those factors, to extract some meaning and sense out of those factors, we do another step that is called factor rotation. But this factor rotation is generally not applicable in confirmatory factor analysis. Similarly, in exploratory factor analysis, we derive or we can compute the latent factor scores also using different approaches. And this is not the general practice in confirmatory factor analysis. So it is generally not applicable. But remember again that it does not mean that such latent factor scores cannot be computed. For example, using MOS, we can follow the method of imputation, and the imputed scores are nothing but similar to what is called factor scores. So that is possible, but in general I am doing comparison that this is generally done but this is not done. As far as hypothesis testing is concerned, I already explained that exploratory factor analysis, we do not begin with any a priori hypothesis because it is exploratory in nature. We don't know beforehand what will be the factor structure, which variables will be related with which latent factor, how many latent factors will be there, we don't know. So there is no point of making any hypothesis regarding the structure of the model. But in confirmatory factor analysis, we begin with a pre-hypothesized factor structure. Similarly, goodness of fit of the model, what the factor structure that we have obtained, whether it is fitting with the data or a pre-hypothesized model, we do not do this in exploratory factor analysis in general. But this is one of the steps, and we do test goodness of fit in confirmatory factor analysis. Though computing goodness of fit indices in exploratory factor analysis is also possible, some of the softwares which have been exclusively developed for doing exploratory factor analysis. For example, there is one open source software whose name is itself factor, and I do not remember which latest version is available, but I think up to 10 version will be available, and that can provide some goodness of fit indices too. As far as the software is concerned, the general purpose statistical softwares generally have one module for doing exploratory factor analysis. But confirmatory factor analysis are generally not part of the general purpose statistical software. though nowadays some of the softwares are including the confirmatory factor analysis also. But when we really want to do structural equation modeling, there are some dedicated software, and I have listed some of the names like M+, Lisrel, Lemos, UQS, SAS, Callis. These are some of the softwares. Now let us move to the actual purpose of this presentation, that is doing structural equation modeling. And the first thing is the sample size requirement. Generally, a reasonably large sample size is required, as it is required in factor analysis or other multivariate statistics. And there are several rule of thumbs. One such rule of thumb is that if the model is not very complex, it is a simple model, then the data on 200 participants may be sufficient to test that simple model. Similarly, another rule of thumb given by Stevens in the book Applied Multivariate Statistics for Social Sciences, that 15 cases per predictor, as it is required in a standard OLS, ordinary least square multiple regression analysis. So if we are doing path analysis or structural relationship model, then the sample size requirement will be very similar to the multiple regression analysis requirement. Similarly, another rule of thumb is that when relationship among the components of the models are strong, then we can go for as low cases as 10 cases per estimated parameters, and that may be sufficient or adequate for testing the model. Some researchers like Bentler and Chow, they have proposed that researchers may go even for a lower sample size, and they recommend that 5 cases per parameter estimate is sufficient or adequate for doing the structural equation modeling. As far as assumption, I have not created any other slide. As far as assumptions are concerned, the um, assumptions for multivariate statistics, many of the assumptions apply here. For example, multivariate normality should be there, and similar other assumptions are there, but I am skipping this. I am directly coming now the common steps that are involved, and I have used the term model construction, though it may not be very popular or common in the terminology of SEM. But I have tried to club three aspects of uh, the or three steps of the structural equation modeling, that is model hypothesis, model specification, and model identification, in one rubric, that is model construction. First we construct the model, and when I am saying model constructions, it means that we have to develop or hypothesize our model based on previous research, our own research experiences. Then we have to specify those model, and finally that model must be identifiable. And that hypothesized, specified, and identifiable model, when it is ready, then we can say that we have constructed a model. And the next step will be then estimating the parameters of those models, that is the regression weights, regression coefficients. If it is path analysis or structural relationship model, then those parameter estimates may be the regression coefficients or path coefficients, and when it is a measurement model, those parameters estimated may be factor loading, though again they are similar to the standardized regression coefficients. And after estimating, we evaluate the model, whether the model with the uniquely estimated parameters are really fitting with the data or not. And then if it is not fitting, then we can again move in an exploratory fashion. And in my previous lecture, I have defined that the three scenarios of structural equation modeling. One is strictly confirmatory. So if it will be strictly confirmatory, our steps will be final model evaluation. If the model is fit, then we will accept the hypothesis, otherwise we will reject. But if we are working in alternate model generation scenario or the other third scenario, then model modification may be permitted, and then we try to modify the model, and modification is generally done by removing some of the paths, deleting some of the variables likewise, and then we again evaluate the model, and we do it in a iterative fashion till we arrive at a best fitting model. And sometimes we may not arrive at a best fitting model, and then ultimately we will reject the model, and we can again think of the theory. It may be possible what we have theorized is not in the correct direction, and then we may develop another theoretical model, and then we can proceed with model testing. And again, if we are doing so, then we will start from model construction and the all the steps. After model modifications, retesting of the model fit, and then we will take a final decision which is the best fitting model to retain. So these are the steps. I will elaborate little bit about each. So model hypothesis is based on earlier research, theory, experience, or a combination of both. We hypothesize how the variables will relate, and this the hypothesized pattern of relationship among variables is the structural relationship model. Or if we are hypothesizing latent variables are linked with some observed variables, then that will be a measurement model. But anyway, the first step is to develop the model hypothesis, to hypothesize the model. And then model specification basically involves translating that theoretical model, translating the theory or the previous research or knowledge into a structural model. We will define the relationship, and then finally we convert those relationship in different multiple equations or in a path diagram. So developing that path diagram or developing that simultaneous structural relationship equations, that may be considered in a very crude sense model specification. So creating a hypothesized model that we think explains the relationship among multiple variables, and we define which variable will relate with which variable. These are examples. So this is the hypothesis that there are two constructs, and I have taken it from Klein. So exercise and say Hardy personality, these two are co-varying, they are interrelated with each other. But these two variables are determining the fitness and the level of stress. So there is an arrow from Hardy to fitness as well as Hardy to stress. And we are at the same time hypothesizing that this will also influence the level of illness. Similarly, exercise is also linked with these three variables. Then fitness is influencing illness, and stress is also influencing illness. Hardy is influencing directly the illness as well as indirectly the illness through stress. So all these paths and models, first based on earlier research, we hypothesize and then we develop. And these pattern of relationship can be represented or converted into terms of equations. So this is basically model hypothesis and model specification. Similarly, if we are working with measurement model, this type of model, this is, though this should be a ellipse or oval, because it is a latent construct. So these three variables or observed variables have been linked with this latent supportive management, and there is a functional group which has been linked with these three indicators. And I have not identified the model. This is model specification. And we also assume that these two latent constructs are interrelated with each other. They are co-varying with each other. This is example of a specification of the measurement model or the confirmatory factor analytic model. After specifying and hypothesizing the model, we enter into the next step, that is the model identification. And this is very important. If we are not able to adequately identify the model may not be estimated and it cannot be tested. Basically, identification is considered as a theoretical property of the model, which neither depends on data nor it depends on the estimation procedure. But we can think that if a model is identifiable, it means that the unique estimates of the parameters can be estimated. So if we can uniquely estimate the parameters of the model, then we have been able to identify the model. This is one way of defining or understanding the concept of identification. So until and unless we identify the model, we cannot test. So I have quoted long that attempts to estimate models that are not identified results in arbitrary estimates of the parameter. But when the models will be identified, adequately identified, then we will get unique estimates of the parameter. Those parameter estimates will be unique. And model identification is done by setting rules. So basically it is a set of rules for whether a model can be estimated or not. For example, if we are working with a measurement model and that measurement model is assumed to be having only one single latent variable, latent factor, then these are the conditions that are required to adequately identify the model. There must be at least three indicators with non-zero loadings. The errors of all the observed variables must not be correlated with each other. And since the unobserved variable is not directly measured, therefore we fix the factor loadings to 1, and this is generally done for scaling purpose. So these three are the conditions for identifying a measurement model having a single latent factor and three indicators. Similarly, for structure relationship models, there are other conditions. So when we are identifying the model, there are three conditions. The one is necessary conditions, which are essential, but mere presence of those necessary conditions will not ensure the identification because they are not the sufficient conditions. Similarly, the conditions may be sufficient. It means If those conditions are there, if we meet those conditions, then model is identified. But the opposite is not correct. It doesn't mean that if we are not able to meet, then the model is unidentified. Therefore, for model identification, we must meet the necessary and the sufficient conditions. And for different types of structural and relationship models, very detailed rules of identifications are given. Generally, the modern softwares help us in knowing, and this is basically a mathematical procedure whether the model is identified or not. So the software does for us, and it helps us knowing whether the model is identified or not. And if it is not identified, then where we can work to make the model identifiable. And if you want a very simple yet complete discussion about the overview of the process of identification, the various conditions and rules, either for the measurement or the structural model, then I would recommend the web page of the David and Kenny, and the link is given here. You can go and visit the site and go in detail what the model identification means and what are the requirements. But for the purpose, I will define that there are three conditions when we identify the model. Models may be either just identified model. A just identified model is one in which there is one-to-one correspondence between the data points and the structural parameters. It means the number of data points and the number of parameters to be estimated, they equal. The number of data variances and covariance equal to the number of parameters to be estimated. And generally, this just identified model is also called saturated model. This just identified or saturated model will yield unique solution for all parameters. But remember that it is not scientifically interesting. Why? Because when the number of parameters and the number of data points are equal, the degrees of freedom will be zero, and therefore with 0 degree of freedom we can not test the hypothesis and we cannot reject the model. So the testing of the model fit is not possible if the model is saturated or just identified. But it doesn't mean that it will not provide the parameter estimates. Parameter estimates will be there, and they will be the unique solutions. They can be interpreted in the same way as done in other cases, but we will not be able to test the model fit. This is the difficulty, and therefore we do not wish to work with just identified model. The second condition is over-identified model, and this is the model that the researchers are interested in. So we always strive to arrive at an over-identified model. In this over-identified model, the number of parameters to be estimated is always less than the number of data points. And as you know, the definition of the degrees of freedom is equal to the number of data points minus number of parameters. So if parameters to be estimated are less than the data points, then the value will always be positive. So if there is a positive degree of freedom, then the model is over-identified. And because of this positive degrees of freedom, we are in a position to reject the model, and therefore this is the model which is interested to the scientist and is of some scientific use. So again, I am concluding that our aim is to specify a model and meet the criteria of over-identification. If it is just identified, then parameters can be estimated, but the model cannot be rejected. And the third condition is under-identified model. And you can guess what under-identified model will be. When data points will be fewer than the number of parameters estimated. An under-identified model is one in which the number of parameters to be estimated exceeds the number of variances and covariances, that is the number of data points. As such, the model contains insufficient information from the input data because the number of parameters to be estimated are higher than the number of data points, and therefore infinite number of solutions are possible. We will not arrive at a unique solution, and therefore this is a model which we generally are not looking for. We are not interested in. So the purpose of model identification is that until and again, if we have to define simply what is model identification, then model identification means uh, uh, or the identifiability of a model means that the model is such that their parameters can be estimated uniquely, and the model can be tested for its goodness of fit and can be rejected. And as you might have noted, it is linked with degrees of freedom. So in terms of degrees of freedom, if the degrees of freedom is zero, the model is saturated or just identified. If the degrees of freedom is positive, then model is over-identified. And if degrees of freedom is negative, then the model is under-identified. I have tried to give one example how we calculate or how we can know the degrees of freedom. Suppose we are working with a structural relationship model, path analytic model, and there are k variables to be interlinked with each other. Then we can define one quantity q, and q is k into k plus 1 divided by 2. This will give you the value of the possible data points, that is the number of variances and covariances in the matrix. And p is the number of parameters to be identified as to be estimated. This is another quantity, and using p and q we can determine. So q minus p is the degrees of freedom. In path analytic model, P generally sums to the number of paths which are defined in the model and the number of correlations among the exogenous variables. Generally, in many models, we correlate all the exogenous variables with each other, but it is not necessary. We can correlate a few, but not the others. Sometimes there are path analytic models in which, and generally this is done at the level of modification, that sometimes errors or disturbances are also allowed to correlate with each other. So those will also be added, and some of these will determine the number of parameters to be estimated, that is the P. And if Q is equal to P, it means the degrees of freedom is 0. The model is just identified. If Q is greater than P, then there is a positive degree of freedom and the model is over-identified, and we are interested in this over-identified model. And if Q is less than P, then it is under-identified model. So, over-identified model is one necessary condition of identification. But remember, it is not sufficient condition to resolve the identification problem. Sometimes we need to impose constraints to get the model identified so that the parameters can be estimated. So this is one important aspect. After specifying the model must be identified. And whenever we will be using M+, MOS or other software, it will help us in knowing whether our model is adequately identified or not. And if it is not identified, then it will generally the software tells that these connections are missing, the constraint is missing, and if you will put those constraints or those connections, then the model will become identified. And until and unless the model is adequately identified, we will not be able to estimate the parameters and test the model fit. Now, once the model have been specified and identified, then we enter into the next stage of analysis, which aims at estimating the parameters of the specified model. And the parameters are the path coefficient, the regression coefficient. Sometimes the parameters estimation may include estimation of the variances or covariances also. So, estimation is basically an analysis. It is an iterative analysis process or procedure which aims to minimize the difference between the sample variance and covariance matrix and the population variance matrix. And for achieving this minimum difference between this model, there are different methods of model estimation. The most commonly used method is maximum likelihood estimation, and almost all software meant for structural equation modeling provide this. Similarly, there is another method of parameter estimation, and that is generalized least square technique. And different Monte Carlo studies have documented that both these methods, the maximum likelihood estimation as well as generalized least square technique, they are fairly good in doing the parameter estimation or model estimation. Nowadays, Bayesian statistics is becoming popular in research, so Bayesian estimation can also be done, and many softwares, even MOS, provides opportunity for Bayesian estimation of the parameters. So, using one of these methods, after identifying the model, we will estimate the parameters. And then, after doing parameter estimation, we will evaluate whether the model that we have just estimated is a good fitting model or not. And then the model evaluation procedure begins. It is basically testing how well a model fits the data. But remember that the researchers like David Kenny also say that these model fit indices, I will discuss some of them in the next few slides, provide a global fit, but the model must be examined for the local fit also. So even when the well-fitting structural model have been achieved, even then we should test the significance of the predictors, the significance of the path coefficients, and if any of the parameter, and that can be done by dividing the parameter estimates by their standard error of uh, standard error, and this will result in Z scores, and Z scores can be interpreted as usual for level of significance, whether the parameters are significant or not. If there are non-significant parameters associated with any path or any variable, it is generally recommended that to enhance the model fit, those parameters those paths may be dropped, those variables may be dropped. This is for structural relationship model or path analysis model. For measurement model, the local fit requires the evaluation of the factor loadings. Whether the factor structure model may be very good fit, but there may be some factor loadings which are statistically non-significant or which are below a commonly agreed cutoff. Generally 0.6, zero point 0.5 factor loading is considered good. If the factor loadings are very small, say 0.3, zero point 0.2, even though they are statistically significant, researchers suggest that it will be better to drop those variables which are having very low factor loading, and that will result in a even better model fit. So this step is required at the level of model evaluation. And then to finally decide whether the model is overall globally fit or not, we use different model fit indices. And these model fit indices can be categorized into three classes. The first one is called absolute fit indices. This basically determines how well an a priori model, predefined model, fits the sample data and demonstrates which proposed model has the most superior fit. So if you are having different model, which model is the best fit? However, remember that calculation of these fit indices do not require any comparison with a baseline or any other model. Its calculation are basically based on discrepancies, the difference between the two models. If the difference between the two models, say the uh, a priori model and the sample data model, and the difference is minimum, very low, negligible, then we will say that the model is fit. So these fit indices are based on uh, this principle, absolute fit indices. They try to determine the discrepancies between the model obtained from the sample and the a priori model. And if the differences are minimum, then we say that the model is fit, otherwise not. And for this, generally the model fit indices are based on residuals or explain variances. If the variance explained by the sample database model is say 95% of the a priori model, then we can say yes, the model is fit. So greater the variance explained, better the model fit. And another category of index is based on residuals. So if we have explained 95% of the variance from the sample model in the a priori model, then 5% is yet to be explained. That is the residual, that is the error, that is the remaining. And some indices are based on residuals. So if residuals are lower, the model fit is better. If the explained variance based indices are used, higher the value, better the model fit. And these are some of the names that I will explain in the next slide. So one of the classical model fit index is the chi-square test. The chi-square test of the discrepancies between the two models. And generally, if the chi-square is non-significant, then the model is considered fit. But chi-square values and its significance is dependent on sample size. So if the sample size will be higher, it is likely that a very small chi-square value may become significant, and then we will arrive at a conclusion that model is not fit. Taking this into limitations, the relative chi-square index was proposed, which is adjusted for the sample size, and therefore the relative chi-square is defined as chi-square divided by df. And if chi-square divided by df is low, say 2 or 3, then we say that the model is fit. Despite the significance of the chi-square, chi-square may be significant, but we will not reject the model when the chi-square df value is less than 3 or less than 2. Similarly, root mean square error approximation RMSEA, as the name suggests, this is a residual based index. So lower the residual, better the model fit. So Spiger has suggested that a value of less than 0.07 of RMSEA suggests a good model fit. But some researchers suggest that if it is less than 0.03, then it will represent an excellent fit. Another index is goodness of fit statistics, GFI. And if the GFI value is greater than 0.95, generally it lies between 0 to 1. And higher values indicates better fit. But the cutoff is 0.95. So if GFI is 0.95 or above, the model is good fit. But some researchers also say that uh, if the value is 0.90, it also indicates a satisfactory fit. Similarly, AGFI, adjusted goodness of fit statistics, has also been proposed, and a value of 0.95 or higher is considered an indicator of good model fit. But some researchers go as low as 0.80. Root mean square residual RMR. As the name suggests, again this is a residual or error based index, but no cutoff has been given for this. So general rule is lower the value of the RMR, better the model fit. And there is a standardized version of RMR, and for this, Hu and Bentler suggest that if standardized root mean square residual is less than 0.08, then it indicates a good model fit. So these are some of the commonly used absolute fit indices for testing the model fit. Another two categories include the incremental fit indices. They are also called comparative or relative fit indices. Why? Because they do not use chi-square in its raw form, but they compare the chi-square values to a baseline, a null model. And remember that in absolute fit indices, I said that no model comparison is done from a baseline or any other model. It only tests whether the pre-hypothesized a priori model is discrepant from the model obtained from the data or not. But here we compare it with a baseline or null model. So they are based on discrepancies from the null model or the baseline model. And these incremental fit indices include norm fit index, non-norm fit index, NNFI. This NNFI is also called TLI, Tucker-Lewis index, and comparative fit index. I will explain these in the next slide. And the final third category of model fit indices are called parsimony fit indices. These indices are basically based on the previous indices. They include the above indices, but with some adjustment in a way that the less parsimonious models are penalized. So the parsimonious model will be rewarded and less parsimonious model will be penalized. Such adjustment is done. And generally, the parsimonious fit indices are used for comparing two models and two non-nested model. Nested model is that suppose we developed a model using 5 variables and then we dropped one variable. Then the 4 variable model resulting after dropping the one variable will be called nested model because it is a subset of the first model. But the non-nested models will be two entirely different yet similar models. So for testing whether two non-nested models are comparable or not, these parsimony fit indices are used, and these are the name I will show in the next slide. So these are the incremental fit indices. As I have already said the name, NFI, if it is greater than 0.95 or equal to 0.95, it tells very good model fit. NNFI 0.95 or higher is a good model fit. And if CFI is also 0.95 or higher, then it is also called good model fit. In parsimony fit indices, the two commonly used indices are PGFI, parsimony goodness of fit index. As the name suggests, it is based on PGFI by adjusting for loss of degrees of freedom. Similarly, the PNFI, parsimonious non-fit index, is based on NFI and adjusts for degrees of freedom. So these two indices are parsimony fit indices and based on the uh, uh, incremental fit indices, but after some adjustment. And remember, there is no predefined cutoff point or threshold labels, but generally it is said that the values should be within the 0.50 region. Another set of parsimony fit indices are based on information criteria and AIC, the Achic information criteria, and the consistent version of AICC. AIC are two examples, there are others also. And again, there is no threshold value for it. Smaller the values, better the model. So if AIC is lower with model A compared to model B, then model A will be called better model, best fitting model compared to B. So these are the model testing procedures. Now, since I have discussed so many names and remembering all the names may be a little difficult, so I have created the slide. What should be the criteria of fit? Just remember that the model fit indices are of three types: the absolute fit indices, incremental fit indices, and parsimony fit indices. Parsimony fit indices generally we use for comparing non-nested models. So when we are doing model modifications or when we are testing alternative hypothesis, non-nested models, then those are more useful. For testing the model fit, then we are having absolute fit indices and incremental fit indices. And as I said, that these fit indices are generally based on either residuals or the variance explained. So, like GFI, AGFI, these are indices based on variance explained. So, if they are explaining 95% variance or higher, they are considered good. So, we do not have to remember a lot. Simple logic should be remembered that if the index is based on explanation of the variance in the model, then 0.95 or higher is good criteria, but 0.90% explained variance may also be considered satisfactory. And similarly, if residual or error-based indices are there, then lower residual means better model fit. Some of them say that if it is 0.07, 0.08, then good. And but if it is 0.05 or lower, then this will tell us that the model is having excellent fit. So this is the simple rule to remember. Now I am coming towards the end. The model comparison and for nested model comparisons. Suppose we have to compare two models and nested models means the other model is derived from the first model. Then there is one approach that is called chi-square difference test. So it is very simple. I have written all these steps. You just read. I am just summarizing that chi-square difference test involves examining the difference of the chi-square values associated with the two models. The one model from which the subset has been derived. So chi-square of the bigger model minus chi-square of the smaller model associated with the smaller DF. That will result in chi-square difference delta chi-square. And then subtract the degrees of freedom of these two chi-squares and then examine whether on that degree difference degrees of freedom the chi-square is significant or not. If it is non-significant, then the two models are not significantly different. But if the value is significant, then we can say that modification has resulted in a better model fit. Another approach is delta CFI, change in the comparative fit index. And Mead and Associates suggest that if delta CFI, again it will be done in the same way. There are two models, so the CFI of the model associated with higher DF minus CFI of the model associated with lower DF, that will result in delta CFI. And if delta CFI is less than or equal to zero point 0.02, then it is representing trivial difference, negligible difference in the parameter estimates among the models. So the models are not different. But if this delta CFI is greater than 0.002, then we can say that the modification has resulted in a better model fit. Similarly, another approach of doing comparison is using root mean square error approximation RMSA 95% confidence intervals. If the 95% confidence or 90% confidence interval of the two models do not overlap, then the models are significantly different. Difference in model fit are considered non-significant if models have overlapping So if the confidence intervals are overlapping, then the models are not different. But if there is a non-overlapping confidence interval, then we can say that the modification has resulted in a better model fit. So thank you very much. And in the next few lectures, I will